Hi, I'm Bob Alsop with ShopSabre CNC. Around here they call me RouterBob. We're going to be cutting out a Christmas lawn display on one of the most popular ShopSabre CNCs, the IS510. You know, the reason these ShopSabre IS series cut so well and have such great edge finishes starts with the base frame. The base frames on these machines are structural steel. They're all welded, so that entire base is one piece. Then you have a tubular steel all welded gantry and tubular steel supports. But now let's look at what makes things actually move. The axis of motion is determined by these precision guide rails, and we use those in all three axes. But you know what really determines accuracy is the machining that lies underneath it. Since we fabricate and machine our own frames, we can control how accurate these machines are. Now let's look at what really makes things move. What creates machine motion are the precision ball screws that we use in X, Y, and Z axis. Now I get asked a lot about ball screws versus rack and pinions, and the answer is really clear. Ball screws are higher precision. That's why the machines that are used to machine the precision frames all have ball screws. If you look at a rack and pinion system, there's some inherent play in it, and that's because it requires 3 to 5 thousandths of clearance between the pinion and the rack. All right. Now, you run into companies that say, oh, well, we saw that because we use planetary drives. Well, they don't understand the engineering because their planetary drive doesn't replace that mesh. So what happens is not only do you have the 3 to 5 thousandths, you have some more play that you've added on. We know all about this technology because we use that on some of our lower end machines. But these are machine tool grade CNC routers, so they have to have precision ball screws. Now, on top of that, we use Mitsubishi closed loop servo motors and matching Mitsubishi drives. The final part of motion control is the control itself. Let's take a look at it. We base the ShopSabre MMP control system on a very robust technology. In fact, MMP stands for Mitsubishi Motion Platform. But there's another part of machine control that's people related. Specifically, how easy is it going to be for one of your operators to learn how to use it? So our real focus on the front end of the computer was that, to make it simple for one of your employees to run this, so you don't have to hire an engineering type employee. Let me show you how easy that is. The thing that really stands out on the ShopSabre MMP operator screen is everything's on a single screen, so it makes it really easy to operate. And the buttons are grouped together, so you can notice these keys actually move the machine in all these different directions at different speeds. You have a group of buttons down here that really are routine things like homing the machine and setting different variables. Over here you have a display of the coordinates. If you notice here, there's a slider for feed rate and there's a slider for RPM, so you can actually make adjustments while the machine's running. This is a program display area here, and this is actually the G code. So all the operator has to do to execute a program is to go File, Open, select the program, then they hit this little button that says I, and it displays the program. So we know immediately what's going to be cut on the machine, and if it displays it, we know that it runs in the control OK. And then it's just a matter of actually executing the program. So we'll hit the green button, and you'll see it run live on the screen. So it's a really, really neat, easy to use operator interface. Now let's take a look at the machine spindle. This machine has an HSD 10 horsepower ATC spindle. ATC stands for automatic tool change. Now the spindle is actually mounted to a tool plate, and there's a lot of engineering involved. In fact, if you look at these two stiffeners, there's an interesting story on those. Engineering wanted to create more rigidity where the tool touches the material. And so they realized if they could stiffen that whole assembly that they would accomplish that. So we use finite element analysis software for all of our design and testing. And this is what came out. And once it proved out, then we went back and we cut some of these out, which reduced the mass. Now, when we're talking about engineering, there's another interesting thing that you'll notice on this machine, and that's balancing cylinder. Now, what happens is in 3D machining, typically the slowest axis determines your maximum feed in 3D. And normally that's always going to be Z. So we realized if we could reduce the weight of the spindle, we could actually raise and lower it much, much faster. And that's what the balancing cylinder does. It neutralizes this mass. So you'll find these machines actually cut in 3D really, really fast. And also that's related directly to drilling, so they drill faster. Now let's take a look at the machining table. This particular IS510 has a phenolic vacuum table. Let's look at that a little closer. These are vacuum ports. There's 8 of them. They're controlled by 4 valves, and they're actually connected to the vacuum plenum, which is part of the machine frame, with large tubes. Then a 4-inch tube goes from there all the way back to the vacuum pump. So we get unbelievable flow in the vacuum table system. Now, something else that's neat about these tables are actually machined with the router heads, so they're incredibly flat. What that means to you is typically you don't have to have gasket between the table and the spoil board. Now, also, while we're talking about the table, let's look at the width here. It's bigger than 5 feet, and I'll explain to you why. It actually measures 77 inches. Let's say you're a cabinet shop and you buy this machine to make kitchen cabinets, and you find out how lucrative the closet business is, and so that becomes a part of your business. Well, closets have a lot more drilling than cabinets, so you say, boy, I wish I had a boring block. I wish I bought my machine with a boring block. Well, that's an upgrade in the field, so you can actually add the boring block at a later date, and that's why this table is so big. Now, there's one other feature I really want to point out that I really like. This has pop-up pins. So there's 5 different pop-up pins. Here's what those do. They enable your operator to just put the material on the table, slide at those pins, it's automatically aligned, the vacuum goes on, when the spindle starts, the pins retract. So it's really, really easy for the operator. Now, let's go design something. I wanted to do a video that used plywood, had a lot of curved parts, and was neat, and I really found something neat. It's a Christmas display you might find in someone's yard. It's a sleigh and reindeer. Let's take a look at that. Here's the sheet of material. It's 4 by 8. It's 3/4 thick, and you can see the different parts. Here's the reindeer parts, and here are parts for the sleigh. And it's going to look really nice when we get this put together. Now, let's dig into this a little bit, and let's talk about how you toolpath a project like this. First thing we have to really figure out is how are we going to hold these parts while they're cut. And of course, this is a sheet of plywood. It's going to be held with flow-through fixturing, which means vacuum is actually pulling through some MDF. And in that case, we have to worry about which parts are the smallest, which ones might have a problem with moving around. And so we want to deal with those separately. Now, if we actually just look at this nest, I see a couple areas. One, this is a cutout in the sleigh, and this is one. And here's a cutout here. And we really want to worry about those moving a little bit, so we'll treat them differently. And this is a pretty small part here and here. So what we're first going to do is we're going to treat those differently. So we're going to use a process called return onion skin. And what that means is that we cut part of the way through, we leave an onion skin. In our case, it's going to be about 30 thousandths. And we do those on all 6 of those identified parts. Then we go back and we cut through those, so that cuts those separate. And that's called the return pass, so that becomes return onion skin. Then we cut the large parts. Now let's go look at the actual toolpaths themselves. Let's open the toolpath tab in VCarve Pro. And you notice we have a number of toolpaths here. First off, if you look at this one that says inside, these are actually the inside cutouts in the sides of the sleigh. And then we have small, so there's the parts that we've identified as small are these 6. The inside cuts in these 2. And these can't really be done with the same toolpath because some of the pieces are cut on the inside and some on the outside. So at this point, those pieces are still held in place by the onion skin. Then we come back and we do the return, so there's the inside return, the small return. After those toolpaths have been executed, the parts are free. And then we come back and we cut the remaining large parts. Now, let's look at that in simulation. Basically, here's what the inside parts look like. And if you notice, those didn't cut all the way through yet. Once again, they're connected by an onion skin. Okay, here's the small parts. Okay, then we get to the return. So here's the inside return. Now you can see it cut all the way through. And here's the small return. And then we do our final parts. And that's what it looks like. Now, let's output the code for the machine and let's go make these parts. Our Sleigh and Reindeer project came out really good. You can really see the accuracy of our ball screw systems of our machine frames and these edge finishes. Now these go to the ShopSabre finishing department, and they're going to be in somebody's front yard for the Christmas season. I hope you enjoyed the video. If you need more information, you can contact us at shopsabre.com. Thank you for watching.